This question states, if we have the following configuration, derive the expressions for displacement across the beam. What is the displacement little v at x1 equals L over 4? So to get started with this problem, we need to have an idea of what the internal shear force and bending moment might be, or we have to go all the way back to the initial derivative, the fourth derivative of the displacement versus x, and set that equal to w. I'm going to go ahead and look at this problem from the lens of the differential integral relationships that we described previously and follow that set of steps to figure out what the internal bending moment looks like, and then we'll perform a couple of integrations. So for this problem, we should probably go ahead and perform external equilibrium. That is a good first step. So our first step here will be perform external equilibrium. And for this problem, we can go ahead and draw out the beam in its entirety, and we can put a couple of forces. We'll call this R sub L, and we'll call this one R sub R. And even though this is a roller on this side, I'm going to say that that can potentially pull down. Why? Because I have this torque being applied in the middle, and it suggests that it's going to probably try to lift off on the right side, and it's going to try to push down on the left side. That's just kind of from intuition with the torque the way it's drawn. So if I am maybe a little more precise here, we'll call that M naught. Okay, we can now go about performing our two types of equilibrium. So if we look at the sum of forces in the vertical direction, we'll see that we've got to have RL minus RR equal to 0. So that's just telling us, we can almost see that from symmetry, that RL and RR have to be the same. And then when we look at the summation of the moments and set them equal to 0, we can say, well, which spot would be a good one to select? There's no kind of completely right or wrong way to do it, but let's just do it at the right. So we'll do so we'll say at right, which we could say, well, would be x1 equal to L, or it would be x2 equal to 0. Okay, so we could even say that, just for clarification, maybe I'm being exhaustive here, but just to give us some familiarity with these coordinate systems that we're introducing and how we're treating these types of problems. So with this set forth, we can go ahead and ignore the force, but we see that we're going to have a minus RL times L. Okay, we see that's going in, at least if Z is coming out. And we have a plus M naught equals 0. So we can say that RL times L is going to be equal to M naught, and so RL will simply be M naught over L. Okay? And we saw previously that RR is equal to RL, so we can also say that RR is going to be equal to this RL M naught over L. So when we draw the shear force diagram, and here we go, we need to think about what's happening at the boundary conditions. So we have this is going to be 0, this is, we'll say, it's not quite, but that's L, and this is X, and then this is going to be V. What's happening at the left side? Well, at the left side, and I'm trying to think, well, okay, this is kind of maybe not the most conventional way to draw these things, but because I still have to have the bending moment diagram, but by convention, when I expose the right side, okay, I have a downward internal shear force, and so these two right here are the convention. This is an external force which I have the option to kind of select whichever direction I want. But the V and the M, the big V and the M, I don't have that option. So we have M naught over L, and that means that the V at the left side, so we'll say x1 equals 0, is equal to just this M naught over L. You see that? Because we have them in opposite directions and there's no bending moment here, so it's just that's got to be what it is. And the bending moment at x1 equals 0 is just going to be 0. On the right side, we can say, so that gives us a value, right? So we'll say this is going to start off at M naught over L. For the right side, so if we're looking at this diagram, okay, then the convention says that that has to go up, and this is convention in Hibbler's book. Bending moment should go like that, and we have the RR going down like that, which is equal to M naught over L. So once again, we see that V of, and we can say x2 equals 0 is just going to be equal to RR, which is equal to M naught over L again. And we can say that the moment at x2, the internal bending moment, is also, again, equal to 0, like we had over here. So this is kind of a boring looking shear force plot. It's just a constant, as we see there. So if we use our integral differential relationships, okay, so remember that we have dm dx is equal to the internal shear force. And we've just said that V is equal to M naught over L, so that M is going to be equal to M naught, we'll integrate x over L, like this, plus some constant. Now, it turns out that this is truth, and this is a general x, we'll say, all right? But there's an interesting thing happening here. We have a coupled moment into the system. And if you remember that if you're going from left to right, if you have the delta m, okay, at coupled moment, okay, is going to be equal to m app, and this is when m app is in that direction. So it's actually, sorry, this direction, okay, which is actually what we often think of as the negative direction. So this one is coming out at us, and so this delta m is actually going to be equal to minus m naught, because when we had the couple moment, and you can go back and look at the derivation if you like, but this is it's opposite, okay, and this is internal. We're relating the internal jump to an external coupled moment being applied to the system. And so in that case, it's m naught, and even though it's kind of in the positive z, it ends up having a jump downward. So when we plot out the bending moment diagram, it looks kind of interesting. Okay, this is 0, this is L. I'm trying to make it kind of right underneath the shear force diagram. We will have at x equals L over 2, or x1 equals L over 2, or x2 equals L over 2. So I can say this is going to be our L over 2. We're going to have a jump of minus m naught. Now, you could say, well, looking at it, it's going to be symmetric. So I've got to start up halfway up, so that'd be like at m naught over 2, and I'm down at minus m naught over 2 when I'm done. So I can say this kind of by looking at it, that this is going to be what you have to get us the delta m of minus m naught. Okay, so this kind of looks correct. But but maybe you would rather have a little bit more rationalization for how we got m naught over 2 and minus m naught over 2. Well, that rationalization can come in from our integration of the v, right? We saw that it's m naught x over L. And then it's got to get to, we had some constant for the initial m, but let's take a look there. Remember, we said that m at x1 equals 0 is equal to 0, and m at x2 equals 0 is equal to 0. So in both cases, we're going to start here, and we're going to start here, where the moment is equal to 0. And I guess I should say that this is the moment vertically that we're talking about. And so that means that c1, if this were x1, that would mean that c1 is just equal to 0. Okay, so c1 is equal to 0, right? So if I say for m of x1, okay, that means that c1 is equal to 0, which means that it's just going to be m equal to m not x1 over L. Well, this is L over L over 2. That's real fun. Okay, L over 2. So if I plug in L over 2 here, what do I get? I just get L's that cancel, and I get m naught over 2. So that makes complete sense. That's what we get. So this is a positive. Also, this is a positive sloping portion of the bending moment. And it stayed positive. So it's still got to have a positive slope. Well, this is perfect because I can keep that positive slope, same slope that I had here, which was just m naught over L, and I'm going to go up like this. So this part of the problem should be kind of a review. And I'm a little embarrassed that that's already taken us a lot of it of time, but I just wanted to make sure that we have this part in place. The next bit is a bunch of math, and it's going to take us a little bit of time to do this math. What is the math going to be based on? Well, it's based on using relationships that tell us what the elastic curve should look like mathematically. And we can write out our relationships right here, which are that EI times the second derivative of the little v, not to be confused with the shear force, this is displacement, is equal to m. So if we go ahead and get started there, we can say that we have EI and maybe we should do left side and right side if we want. I mean, there are multiple ways to kind of do this out, but let's see. Let's say, okay, so the left side we'll have, in terms of x1, and the right side will be in terms of x2. So let's first write out the equation for m left side, and this is going to be a function of x1, and we can see, like we just wrote it here, it's just m naught x1 over L. Okay, so m naught x1 over L. And on the right side, okay, I'm going to write an interesting expression. Well, maybe it's not that interesting, but we've got to get down to minus. And so if I'm going from the right going to the left, this is actually a negative slope. So I'm going to have minus m naught x2 over L, just like that. And now we've got to integrate this expression. So we can, on the left side, we can say, and I'll try to, I guess, make it a little bit more clear, that we have now the integral of this would be the integral of this expression on the left side. And that's going to be the m naught x1 over x1 squared over 2L. And we'll say plus, well, we had a C1, so we'll go ahead and we can do C1. I'm okay with that. And then over here on the right side, we're going to have EI displacement, okay, like this. And I guess, yeah, it's probably okay to do, we'll say that's a little v1, this is going to be a little v2, and we'll do that like that. This is going to come out to be, maybe I should cheat a little bit and move this over. Just like this. Like that. Okay? And how do I solve for C1? How do I solve for C2? This is maybe something that we can think about now, or we can get to a little bit later, but we don't, I haven't named any boundary conditions. So let's talk about those boundary conditions before we go further. Okay, so boundary condition, or boundary conditions, and also continuity conditions. So we know that v1 of 0 is equal to 0. That's the little v now. We also know that little v2 of 0 is equal to 0. Not super helpful at this phase of the game, though, because we have a first derivative. And so that's, kind of unfortunate. There is, though, a condition that we could consider using, and that has to do with the slopes. Okay, so there could be some slope at this location, all right, where I have x1 equals L over 2 and x2 equals L over 2. Okay, and so yes, there's a discontinuity there in the bending moments, but it does get up to that point, it does get down to that point, and so what we can say is the slopes at x1 equal L over 2 and x2 equal L over 2 we'll have some continuity. And if you remember from class, it's an interesting relationship Remember we talked about how if you had something sloping like this, and this is x1, and then if this is x2 coming like this, notice that the slope here, it's going down. So with respect, so at this location, shall we say, and this is v, little v, we could say that, and this is little v, we could say that at this location, let's just call it, I don't know, A, we could say that the d little v x1 at x1 equals A, right? This is going to be less than 0. And if we're coming from the right side, we could say that the derivative with respect to x2 of the displacement coming from the right side, this is greater than 0. And more formally, we can say that even though we don't know exactly what the quantity is, we can say that they're an equal magnitude, but they have opposite sign. Yeah, I guess I can make that a little more formal. You see that? So the boundary condition that we can use here, since we're interested in derivatives, going from the left and the right, we can use the boundary condition that, or this is a more of a continuity condition, is that the derivative of v1 with respect to dx1 at x1 equals L over 2 is going to be equal to the minus, the negative of the derivative of v2 with respect to x2 at that location. Okay, so what happens when we plug these values in? Okay, so we have here an m naught and x1 L over 2, so that will give us L squared over 4 and over 2, so that's going to be, and then divided by L, so that'll be give us an m naught over 8, just like that. Okay, you see that? Plus C1 is going to be equal to the minus of this. So minus the m naught x2 squared. Okay, so this will also be a minus, so it's going to be minus, and we'll have that again L over 8, and this will be plus C2, yeah, like that. And so we see that we get minus, minus, these are going to cancel out with each other, so we just get that C1 is equal to minus C2. Okay, so we haven't exactly solved our problem yet. Okay, but we have we've gotten ourselves another kind of tidbit of information as we keep going. All right, so now we can go to the next integral, and we'll integrate both of these expressions, left side and the right side, and we'll have that EI is going to be, times, or EI times little v1 is going to be equal to m naught x1 cubed over 6L plus c1 x1 plus, we'll call it c3. And on the other side, on the right side, I'll give myself a little more space. Sorry for those of you who are writing on paper and running out of space. we'll say that EI times little v2 is equal to minus m naught x2 cubed over 6l plus c2 x2 plus c4. Okay, and in this case, it's probably not a bad idea to look at this boundary condition that we wrote up here, that the v1 0 is 0 and v2 of 0 is equal to 0 as well. Okay, so if we plug in, okay, v1 at 0 is equal to 0, and we plug in that v2 0 is equal to 0, then we see that c3 is equal to 0, and we see that c4 is equal to 0. Yeah. So that's good, but we still have our c1 and we still have our c2. Okay, so this boundary condition is kind of interesting, but it doesn't help us get where we need to be. So it's almost like, okay, thank you. It was nice to think about, but we need something a little bit more, another continuity condition. Well, what can we do? Well, just like the slope, okay, at x equals L over 2, right? So if we come back and we think about what's happening here, the slope at x equal L over 2, x1 and x1 L equal L over 2 and x2 equal L over 2 for the v1 and the v2, that we said, okay, it's equal but opposite. That's truth, but we can also say, you know, the displacement there has to be the same as well. So we can come up with yet another continuity condition. Okay, so another continuity relationship where we say that the v1 at L over 2 is going to be equal to the little v2 at x2 equals L over 2. And in this case, we don't have, it's not a slope situation, it's just that is where they are going to be equal to each other. So we can plug in those values here and set these two equations equal to each other. So if that's the case, what do we see? We see, okay, that we can plug in m naught. So let me change colors again. So this is for the left side. We have m naught, and then this is going to be x, or so L cubed, and 2 cubed is 8. So that's going to be 6 times 8. That's going to be 48 in the denominator. So, and then we have an L under here, and we had L cubed in the numerator. So this will give us at, okay, this condition where we have, we're at L over 2, so we're going to have m naught L squared over 48 plus, now we have our C1 X1, so we don't know what C1 is, but we can say that the X1 is L over 2, so we can say, okay, C1 L over 2, all right, and that has to be equal to the displacement. And of course, we're saying displacement, but we have the EI, but you know, we're kind of canceling that out on either on both sides, or dividing both sides by EI, but then canceling it out. So then we got to figure out what's going on over here. So L over 2, we have a minus m naught. Okay. Once again, L squared over 48. And then we have a C2 times X2. So that's going to be C2, oops, just like that. Okay. So when we plug these equations in for each other, what's going to happen? Well, um, we can maybe we can play around with things a little bit here. We have the C1 equals minus C2, right? And we have so we're able to use this continuity condition that we had previously with this new continuity condition, all right? And it can help us out a little bit to figure out two equations, two unknowns. So this is gonna, what's half of 48? That's 24. So we'll have then that m naught L squared over 24 plus C1 L over 2. And we can say, okay, C2 is equal to minus C1. So we could say that we have a minus C1 L over 2. Okay, so that's making use of it. And we have the now we can put that over, and we just or we can move this over, but either way we can say that C1 is going to be equal to minus m naught L squared over 24. And we can say that the C2 is equal to m naught L squared over 24. So we're pretty much able to write out the whole expression now. Okay, so the left side, so for x1 pretty much less than or equal to the L over 2, okay, we can write this expression right here, EI. Okay, so EI V1, little v1, is equal to m naught x1 cubed over 6L plus, now we have our C1, which is the minus m naught L squared over 24 times x1. So maybe I'll just change that to minus. And we said that C3 is equal to 0. For x2 less than or equal to L over 2, we have that EI lowercase v2, okay, is going to be this expression that we have over here, minus m naught x cubed, m naught x2 cubed over 6L, and it's going to be plus m naught L squared over 24x2. Okay? So this is the elastic curve, and it will allow us to plug in, right at the very top. It said what is the displacement little v at x1 equals L over 4. So we have to use the left side, of course. We use this equation over here, and we can write for, let me change colors again, for x1 equal L over 4, we can write that EI V1, or maybe I'll write it now since I was asking for this. Then we want to write 1 over EI, and we can write, okay, so 4 times 4 times 4, that's going to be 64. That's, okay, so 64 and 6 times 64, that's 128 times 3. I'm not quite sure. 3 times 128. This is a little bit embarrassing. Okay, and I gotta, so that's Yeah, okay, right, I knew that. Okay, so that's going to be 384. All right. Okay, so we have now a m naught, and we'll have our L squared over 384. And this is going to be just x1. So this is L of 4 times 24. That'll be 96. So that's going to be minus m naught L squared over 96. Okay. And yes, the 496, 490. Okay, so there's 4 of these going to that. So that's going to be 1 minus 4. That's 3 over. Okay, so this is going to be equal to um, minus m naught L squared. I guess 3 of them over 384 EI, just like that. Okay, and so that should be the result we're looking for. Now we did all this, we did all this math, okay, and it is long. And if you've stuck around for this, that's impressive without fast forwarding. Um, what is really the curve though looking like? You might ask yourself that question. So, I've got these kind of nice expressions, and you can see uh, they're like to the third power. So, what kind of behavior will look? Well, let's just come back here and let's look at this and let's draw it. We know that the displacement over here is going to be 0. We know the displacement over here is going to be 0. We know that the m over here is positive. So the curvature has to be positive for this entire time. Okay. We know that the that the curvature on this side, it's negative because we have a negative moment here. So if we think about what's really happening, we can draw something that looks like this, okay, which describes the positive curvature that we see here. And then we can draw something that looks kind of like this, that describes the negative curvature on this side. Now, this is not perfectly, obviously my expressions are not, my drawing's not, perfect here, but that gives us a rough idea of the behavior that we expect given the positive moment, okay, that we have in x1 up to L over 2, and the negative moment that we have from x2 up to L over 2, and that also satisfies the boundary conditions that we've been discussing. That was a lot of math, and I hope that it was somewhat clear and that you found this example useful. Thank you for watching.